Welcome to my presentation. My name is Jan Horacek, and on behalf of my colleagues, I would like to present to you innovative concepts for extreme heat load tokamak divertor. It was done with two different groups, liquid metal divertor simulation by these people in Czech Republic, Prague, and the steam experiments also mostly in Czech Republic, Prague, in tokamak Compass, by myself and my students Vašek Semírovský, my wife Anna Horacek, and many engineers and colleagues. I will speak firstly about why must plasma-facing components survive heat fluxes much higher than 10 megawatt per square meter, why it is necessary. And then that the liquid lithium and tin divertor can survive extreme heat loads, especially transients, via vapor shielding and self-healing. However, they cool and dilute the core plasma, which we don't want. And that's why I'm running the simulations. And these simulations also show us that we need innovative plasma-facing components so that we are running this steam experiment. The predicted and survived steady heat loads are shown on this graph. On the bottom are the predicted plasma divertor heat fluxes in logarithmic scale from 1, 10, 100 and 1000 megawatt per square meter. And this is shown here that for ITER tokamak, which is the future device that we are going to, the naturally flowing plasma flux is for high magnetic field will be given by the so-called lambda Q decay length at the outward midplane. The plasma concentrates by extremely strong magnetic field to tiny little area on the divertor to area about 0.5 millimeter size at the outer midplane. Then it's increased by flux expansion, magnetic flux expansion up to a factor of 7. So it will be 7 times more. But this is not enough. So in fact, if you just take this value without much radiation in the plasma, you get to heat fluxes around 200 megawatt per square meter. And this is way too much. It's much higher than what survived cooling capability is achieved and planned for ITER. So we know that we have to detach it. We have to radiate large part of the plasma. But usually people radiate about 70% of the plasma. So you decrease it down to about this level. It was just achieved just recently in 2021 on ASDEX upgrade that impurity seeded very well controlled X-point radiator can decrease it by a factor of 20 down by real-time, very sophisticated way. And the question is whether it can be really extrapolated to future tokamak. I hope so. It would be very nice, but this has to be shown. There's another approach is to assume that the turbulence, which is shown here in this sketch in this graph, that the turbulence in large enough tokamak and large enough magnetic field will be much stronger. So it will increase the natural heat flux by order of magnitude up to 0.5 centimeter. And this would then, the detachment would work very well, and you can get down to about 10 megawatt per square meter level for Q equals 10 fusion power plasma. But this is very questionable because this cannot be verified experimentally until ITER is built, because this is a new turbulence effect, which is valid for large enough tokamak with large enough magnetic field. There's another approach, alternative divertor magnetic configurations, which are being studied in Europe. However, what was already measured on Alcator CMOD were values between 50 and up to 100 megawatt per square meter perpendicular to the surface in attached plasma. So there is wide probability that the turbulence predicting does not work, unfortunately. So there are other predictions for even more crazy values here in these papers. And there has been lots of effort in the fusion community to decrease the heat fluxes by these techniques. Myself, I was predicting value about 10 megawatt per square meter and Q equals 0, so without any fusion in L mode plasma. So I quite believe these scaling predictions, unfortunately. So the survived cooling capability of heat shields, which we know nowadays, is shown here. So for example, the heat shield of a space shuttle, which returns from the orbit down to the atmosphere, is about 1 and 2 megawatt per square meter. That's this nozzle, extremely large heat fluxes. And then ITER divertor can survive around 16 megawatt per square meter for a long time and about 20 for about 10 seconds. So this is kind of hard limit. Maybe here hypervapotron may be a bit better, but still we are away from what we need. Hopefully not, but it's quite risky, I would say. The sun surface is about 60 megawatt per square meter. And then we know that liquid metals can survive more. However, if not partially cooled, its vapor and droplets disrupt the plasma. That's what I'm going to show you in a moment in my paper. And in my opinion, there was not enough effort put into improving the heat shields, whilst quite a lot of decreasing the heat fluxes. And the good news is that we have a steam heat shield, innovative plasma-facing components, where we survived probably values around 100, and I will explain you later how we did it. Compass Upgrade is a new tokamak in Europe, which we are now building in Prague, Czech Republic. And it's based on a very strong magnetic field. It will be up to 5 Tesla magnetic field thanks to copper-cooled coils. And it will reach up to 2 megaamperes, even though it's a relatively small tokamak. It's a medium-sized tokamak. The power will be, however, very high. And in attached divertor, we can reach up to 100 megawatt per square meter according to our scalings. So this would be a very good way how to test these innovative new techniques. Then on top of it, we have ELMs, we have disruptions, which are heat shocks from the plasma, like regular heat shocks. And we know that tungsten melts already at nearly 1 megajoule per square meter. And this is values which are predicted in this very simple scaling, but very useful scaling by Thomas Eich, where you have data points from for many tokamaks, including Compass, our own measurement, and also my measurement from JET, just last year published, where the values are already at megajoule per square meter, parallel to the parallel to the magnetic field. So if you put it perpendicular, you already melt the tungsten, which we shown already in 2014 in the Jan Cannon paper, when we melted the jet lamellas. And we predict, based on this simple scaling, we can predict the values for ITER about 15 megajoule per square meter, which you decrease by a factor of 20 thanks to magnetic field inclination, which means that you get to value about 1 megajoule per square meter, which means that the whole entire divertor would melt every millisecond. So it means 10 times or 100 times per second. During 1 millisecond, it would be melted and resolidified, and it will change the shape of the divertor if we don't do anything significant with it. We know that liquid metals can survive this. QSPA device in Kharkiv in Ukraine was showing to survive up to 4 megajoule per square meter without any damage. Unfortunately, until it was damaged by the Russian army in 2022. But unfortunately, it's splashing quite a lot of tin into the plasma, which is okay for the LMD target, but it's not okay for the plasma itself. What we showed in 2019 on Compass, for the first time, we were testing liquid metal little module on the bottom of the divertor, just 4 centimeters large module. We put it as perpendicular as possible to the plasma to receive as high heat flux as possible with our relatively weak plasma, let's say. So we achieved values between 12 and 15 megawatt per square meter without any damage. No damage for the lithium-tin alloy plasma-facing component. And it survived even ELMs in the H mode and vertical displacement event disruption. The plasma was not affected by this, even though we saw quite a lot of radiation from the target. And there were no droplets splashing. And also we observed release of lithium and no tin, which is very important. We developed a program on Compass to sustain extreme heat low density liquid metals. So we started in 2018, where I published this paper for simulations, heat LMD simulations. Then we did the experiment itself in 2019, and then we measured the infrared camera surface temperature and compare it with the output from heat LMD model. And it was very well comparable, which means that the heat conductivity, conduction inside the target is the most dominant part, and that the lithium vapor shielding was pretty negligible in this case, unfortunately, because then we could not really quantify it. But then comparison visible camera with the bit1 code showed also nice correspondence of 6 centimeter large cloud of radiating plasma, because that's the mean free path of it. And then also the output of visible camera was compared with Aero 2 simulation, just now submitted to Plasma Physics and Control Fusion. And then, because it was relatively successful, this comparison, we used the same code using the same data from divertor probes with very high time and space resolution, and rescale them towards Compass Upgrade, which has much higher power, low density, but we know how much, thanks to the scalings, we know how to do this. And then it yields, using the same code, the amount of vaporized and sputtered lithium and tin particles. And this then goes into the main plasma, into up to separatrix, and then using the SolPS simulations and error code, it yields input into Aurora, which calculates using facet diffusion coefficients the amount of radiation in the plasma. So how much it cools down the main plasma and how much it dilutes it. And this I'm going to show you in a moment. Unfortunately, it shows us that we need some better cooling of such a liquid metal plasma facing component. Otherwise, we will have problem, especially for tin. For lithium, it's probably okay. But before showing you this, I will explain a little bit more about the heat LMD simulation. So it's based mainly on heat conduction in 3 dimensions. It uses data from divertor probes with very high time and space resolution. So here you see one elm, another elm. This is the inter-elm period. This is a space coordinate along the divertor for heat flux, temperature, density, and so on. And we use the scalings which are described in these scientific papers. And then this determines the surface temperature, and this determines the evaporation and sputtering according to these well-known rules, which are described in my last paper, nuclear fusion. And then what is sputtered and evaporated is partially put immediately back thanks to prompt redeposition. This is especially true for tin. So most of the particles of tin goes immediately back to the surface by within 1 Larmor radius, but only at high temperatures, so above 10 electron volts. So for detached plasma, which has very low temperatures, this unfortunately doesn't work. It means that detached plasma really releases a lot of plasma, a lot of particles into the plasma, which is then put into error code, which calculates how much goes into plasma before, in fact, it's locally shielded using this lithium and tin radiative losses in the just nearby the divertor target. Right. So I'm going to. So what goes into error is the structure is shown here, as I said. So we can run error only for one case because it's a heavy code. So I give in that this is the amount of lithium and tin going into the plasma nearby divertor. And this is the separatrix flux. And you see that it's by 3 orders of magnitude lower, or even 4 orders of magnitude lower for the case of tin. And then, unfortunately, even this is too strong. So even if you decrease it by a factor of 10,000, the amount of tin particles, you get nearly 1 megawatt of radiative power with only 2.5 megawatt going to the divertor. So like one third of what is going into plasma. So it means that you are getting very close to the disruption limit, radiative collapse, in fact, for the case of tin. For the case of lithium, it's not the case. The line radiation losses are very negligible. There is, on top of it, there is Bremsstrahlung, which is of the order of 0.1 megawatt, but we have to calculate it more properly. But still, it's quite negligible. And we get negligible core concentration of 1%, which is much less than 25%, which is the limit, let's say. So this is what we believe can be simulated for one particle parameter in the divertor. The heat LMD can be run not only once, but thousands of times. So I could produce a scaling. It means we are not certain what the plasma will be in our future tokamak. So I vary 5 different divertor parameters, which is divertor power, total divertor power on the full toroidal divertor around the tokamak, the thickness of the capillary pore structure, the electron temperature between 5 and 50 electron volts at the strike point. Then I vary the time over which it's exposed and also presence of elms, yes or no, if they are present. So it increases by factor 3.7 the scaling if the elms are present, or more in this case. And I vary also the alloy. So this is lithium tin alloy or tin. And also I vary the way how I cool down the backside of the target, because here is the capillary pore structure with lithium tin. And then there is copper below it, which cools it down. And this is very important, especially for 1 second plasma. But if the plasma is not exactly 1 second long, then you either have to include this additional multiplication factor by time with this exponent. This exponent, unfortunately, is not a constant, but it's about half or somewhere around it, depending on the plasma parameters. So it rises nearly linearly or even more. But it also depends on what kind of cooling you imagine. So this was the case for cooling using just a piece of copper. If you put there no cooling, no backside cooling, then you get these empty triangles. So for the case of lithium tin, it gets into some saturation just because of the evaporation of the lithium. So in fact, it's nearly in steady state. But for the case of tin, and it of course increases the amount of lithium released into plasma, but still you are below the limit, yeah, well below the 10% core dilution limit, and the radiation is pretty negligible. In the case of tin, it's unfortunately not the case. You increase the amount of sputtered and evaporated particles of tin by 3 orders of magnitude, and you get already above the limit very quickly within fraction of a second. So if there is no cooling, if there is cooling, full water backside cooling, these are the filled triangles, you see that the data are pretty similar to the case of just temporary cooling by just a piece of copper. It means that 1 second plasma is quite the same as if you cool it down perfectly using water. But this also shows us that if we want to use it for steady state, like running it not for 1 second, but hours and years, we need, of course, the water cooling. But in this case, the amount of energy which has to be released from the backside is really huge. These are these numbers in megawatt per square meter. And this is in fact explained here. So you get the temperature profile where on the surface for lithium tin alloy, I think it's the case, I get about 550 centigrades. Then the thermal gradient below the surface gives me that there is about 27 megawatt per square meter flowing to the backside of this target, where I assume that I have 0.5 millimeter capillary pore structure and then 1 millimeter the copper. And at the backside of the copper, I have some perfect cooling. The perfect cooling keeps the temperature constant at 100 centigrades, but it has to remove, in such a case, 27 megawatt per square meter, because only 5 is lost by vapor shielding on the surface. So it means that we are getting to limit of the water cooling, because normal ether-like divertor, which I showed in the beginning of my talk, cannot extract so much heat power flux density. So it's a big challenge. And that's why we started a project which is called Innovative Water-Cooled Plasma Phasing Components for Extreme Steady Loads, which is used which is, I hope, not useful only for liquid metals, but also for other systems, where we did it purely experimentally. So we developed a new structure based off copper, where there is water flowing in it and extracts the heat very efficiently. What we achieved so far was that we could cool down 27 kilowatt power of our air plasmatron for nearly 1 minute without significant damage on the surface of the cooling component. And we measured that the value which was put there was 31 megawatt per square meter. This measurement was quite tricky because we had to take a piece of graphite and smash it with the same plasma and measure with infrared camera the footprint on the surface and use the heat conduction simulation and compare it with the infrared camera. And from this, we derived that there is 31 megawatt per square meter. In another experiment, it was the first experiment we did. In another one, we did it better. And we could do 29 reciprocations with 15 seconds plasma. In total, it means 7 minutes exposure with weakly rising power up to shallow damage, where we extracted 36 megawatt per square meter. And then we did another experiment just few weeks ago, where we believe we went up to 66 or even above 100 megawatt per square meter for quite a long time, for a few minutes. So that's what we achieved so far. We didn't believe it, so we tried to verify the heat flux using a different technique. So in front of the target, we put there a piece of graphite with a hole in it, and then the plasma just flows through it and concentrates inside this hole. And then we said, okay, all the plasma exchanges this energy at this circle below the hole. So if you divide just the power which is absorbed into water by the area, you get 80 megawatt per square meter, which would be quite fantastic. And it survived for 8 seconds until the graphite exploded by thermal expansion. But unfortunately, then we did simulations using ANSYS Discovery that, in fact, it doesn't do this. So the plasma goes here. It does not give its energy in this circle. It does it away where the exhaust, through the exhaust gap with 5 millimeters. So in fact, we cannot believe this value. But what we believe is the measurement using the graphite, and this is shown in this graph, where well-known graph for the ether tungsten divertor, where you have flowing water with 440 atmosphere pressure and 10 meters per second. You have such a dependency of the time, exposed time, in very strongly logarithmic scale with respect to heat flux density. So, and these are the measured data. So in fact, if you expose the with plasma for 1 hour, it can sustain at maximum 25 megawatt per square meter, and then it would crack due to recrystallization and the length of the exposure. And this was measured by 2 different groups. What's achieved using the liquid metals was values much lower than this, much shorter times, like fraction of a second. That's also what we did on Compass, really short times, unfortunately. And already above 10, 12 megawatt per square meter, we get problems. And what we achieved in Germany in 2022 was even much lower heat fluxes and shorter times. But what we did now with our steam experiment, we got much above these values. We believe to get to the recrystallization limit already in spring, and now in September to much higher values than this, probably about 70 megawatt per square meter or more for 7 minutes. But this has to be still verified. What we see with the liquid metals, so this I would say is quite successful, and we will continue with this. What I wanted to still say is problem of spitting and splashing of tin, that it's a big problem for tokamaks, because the heat LMD codes does not account for spitting or splashing, but it releases much more atoms than sputtering and evaporation. I calculated it would be more than this if the droplets are larger than 0.1 millimeter, because they contain 10 to 16 atoms. This is not a problem for lithium because it has very low atomic numbers, 3. So the allowed concentration is 25%. It just dilutes the fusion power. But for the case of tin, it's a very big problem because it has huge atomic number. It means only 0.03% is allowed in tokamak, the concentration. Otherwise, it would go to radiative cooling collapse of the plasma, in other words, thermal disruption. And what we saw on Compass in 2019, that lithium splashed quite strongly for us, but it was because of oxidation, which you can avoid if you do it more properly, let's say. And still, our plasma didn't care about it. We saw splashing, we saw a lot of radiation, but the plasma was still okay. It didn't cool down. Lithium tin is much more dangerous because it contains the tin. And fortunately, we didn't see any spitting because it did not oxidize. That's very good. And because we did not achieve more than 900 centigrades because our plasma is too short in time, unfortunately. So we were quite lucky that we did not exceed this limit. And this limit we just saw in June this year in Madrid on OLMAD experiment, that weakly damaged lithium tin target, exactly the same one, started to spit very strongly above 900 centigrades. And the amount of the droplet is pretty high, 1 droplet per millisecond from the target, which if you extrapolate it to Compass, it would mean nearly 250,000 droplets per second. And it would be comparable to sputtering and evaporation if the droplets are larger than 0.1 millimeter, which is quite the same size as the CPS mesh, so that's quite possible. We have no idea what the droplet size is, so this should be measured. On Aztec carburetor, the spitting of tin, we saw macroscopic splashes really at already this value of megawatt per square meter, 5, and it already increased the core radiation by 40%. So we were really decreasing the power in the plasma by a lot, even though the target covered only 0.1% of the divertor. So it was really tiny object. So if you extrapolated the full toroidal divertor, you should multiply by factor of 1,000, and this would be out of question. We probably know now why this happens. This was Jos Holte, 2 papers published on this. It's probably the champagne effect. It just bubbles out from the hydrogen bubbles out from the tin. And this is something which would be probably quite difficult to avoid. So far, nobody figured out how to avoid this. So tin seems to be quite dangerous for tokamak. So this is my summary here, where what I was speaking about, that ITER may have low heat fluxes, less than 16 megawatt per square meter, which is the limit of the ITER divertor as it's designed for now. But there is a big question mark whether this can be really achieved to be so low, because there are many experimental proofs that it may be quite much higher than this. But let's hope for this, because it is designed, it is now going to be finished, and hopefully we can do as much as possible to avoid these problems. But we should think more into future, because there is such a risk that it may happen to other tokamaks in future in fusion machines. So that's why we developed this liquid metal program, which is shown in these, which is published in these papers, where we did experiments on compass, then do simulations on compass upgrade, which I'm just now publishing in nuclear fusion. And I see that the heat fluxes in medium power HMON will be about 32 megawatt per square meter in attached plasma. So we can achieve really these power densities on our medium-sized tokamak in Prague, Czech Republic, and test new technologies. So either liquid metals or together, I would say, that would be the best, the innovative water plasma phasing component together with liquid metals, because liquid metals is the only way how to sustain extremely strong heat shocks, like transients, disruptions, and ELMs, and together combined with water-cooled innovative plasma-facing components, they should sustain also the long-term operation, because otherwise they would evaporate and sputter too much if the surface is not cooled as strong as possible. So I thank you for your listening, and I would be happy if you write me on my email horacek@ipp.cas.cz.